Okay, so we saw how to use Euler's method to graph a solution to a slope field. It's a long, tedious, reiterative process, and it's not all that precise when we're doing it by hand because our step size needs to be fairly large. So what I've done now is I pulled MATLAB back up, and I have our slope field for dy dx equals x minus y showing, and I am going to show what the solution would be if we're doing a step size of 1. And let's see, we'll make a number of steps equal to about 5. And let's see what happens when we start. Oh, by the way, we're going to start at the point 2, 1. All right. And we're also actually, we're going to simultaneously do this starting at the point 0, 2. So let's see what happens when we start at those 2 points. Whoops, I need to show the solution when I run it, or it doesn't show the solution. And method 1 is Euler's method, okay? Oh, that's sort of interesting if we look at the first solution. Since we started on the asymptote at 2, 1, it looks like there was yes, we had, that's where the slope would be 1. We stayed on the asymptote, all right? With the second solution, we can see we didn't stay anywhere near the slope field when we used a step size of 1. Now, if we were to change the step size down to something small, which we wouldn't want to do by hand, like 0.05, so that's 20 steps per unit, and change this to 50 steps in each direction. Now let's see what happens. Our solution looks much smoother, all right? And let's actually go to 100 steps in each direction. Okay, so if we make that 100 steps in each direction, we'll see that it goes off of the page. So if we start on the asymptote, we'll stay on the asymptote. You can see the other solution approaches the asymptote, and as we go off to the left, it shoots upward. So we can see the shape of a solution in there. Let's put one more solution in that's off of the asymptote below. Let's try the point. Let's go with 3. Oops, not 4. 3, 0, and that will put a third solution in there. And let's run it one last time with that. So we'll see our original 2 solutions being graphed. The computer can do it much faster than we can. And there's a third solution. You can see if you start below the asymptote, it stays below the asymptote. Now you might realize there's some problems here down here in the where the graph gets really steep. It appears that our curve has actually crossed over the little slope lines. Okay, it's crossed over the slope field, which it should never do. It should run parallel to the slope field. This is maybe not the best method. In fact, let me change the equation, and we're going to see how Euler's method doesn't really work so well. If we were to go to the equation, let's say, let's do x divided by y. Yes, so let's see what happens when we do that. You can see we just got a crazy answer over there. Okay, so the slope field, first of all, it's changed because our function now dy dx equals x divided by y. And you can see we have some crazy answers. Okay, now everywhere that this gets crazy, hopefully you can see my cursor here, it's where the slope is very steep. And what happens when we use Euler's method, when the slope goes to infinity, which this program actually limits the slope to being 100 at most, plus or minus 100. But when you have an infinitely large slope, Euler's method says that as x changes by anything, y will change an infinite amount. So you get these big jumps in the line. Because we limited the slope to 100, it didn't jump infinitely much the way it actually would using Euler's method whenever you're on a slope line that's infinite. So I put in another method that always makes the step size the same, regardless of whether you're heading up, down, left, or right. And it adjusts this so that we can actually see solutions in the slope field, even when the slope gets very or even infinitely steep. It will limit how far it steps in the y direction, so that you never step further in the y direction than you would in the x direction. All steps are equal in length, regardless of how big dy dx is. But typically with Euler's method, when you have large slopes, the y changes become very, very large as you're trying to show your solutions. So MATLAB can easily plot solutions using Euler's method or this improved method within a slope field. When we go to sketch these by hand, we're going to, avoid having those infinite jumps that Euler's method could lead to.